Other words, the quantum randomness will show up more in the height of the waves. Quantum randomness is a fact of life. It can't be eliminated, but it can be shifted. Much as you might move clutter from your bedroom floor to your closet, the chaos isn't gone, just out of sight for the moment. Plus, the goal isn't to eliminate noise completely, but to get the best signal-to-noise ratio possible. That's a pretty good overview of how LIGO works. So, what has it discovered? As I mentioned earlier, LIGO detected its first signal in 2015, named GW150914. Scientists studied the data and learned that it was caused by the merger of two black holes about 1.66 billion light-years away. These black holes, which were 29 and 36 solar masses, became a binary and spiraled around each other until they merged and released a blast in the final 20 milliseconds that was so powerful. Now, get ready for this number because this is what the scientists actually think. It contained 50 times the combined light power of every star in the observable universe. At the risk of sounding crude, that is nuts. I've read this fact many times over, and I still cannot comprehend what it means. Yet after traveling for 1.66 billion years and finally reaching LIGO, the disturbance was so faint it moved LIGO's 4-kilometer arm 1,000th of the width of a proton. To visualize this, imagine the distance between us and Proxima Centauri and changing it the width of a human hair. That is the level of precision LIGO was able to detect. If that's not one of the most astonishing feats in human history, I don't know what is. And this was just the first gravitational wave LIGO detected. The second detection occurred 3 months later in December 2015. That signal also came from a black hole merger which took place 1.4 billion light-years away. Over its initial 3 runs, LIGO recorded more than 80 black hole merges. And in August 2017, it detected the merger of 2 neutron stars named GW0817. This signal was notable for being the first gravitational wave to be cooperated by electromagnetic observations from 70 observatories across the planet. This was a breakthrough not only in gravitational wave detection, but in multi-messenger astronomy. It turns out LIGO was just warming up during these 3 runs. As of May 2023, LIGO has begun its 4th run with better sensitivity than ever. After its latest round of upgrades, which kept LIGO offline for 3 years, the observatories now have more reflective mirrors, better mirror suspension, and improved light squeezing with lower quantum uncertainty. And this time, LIGO also has the support of Kagura, a new interferometer observatory in Haida, Japan. Kagura is located underground, making it the world's first subterranean gravitational wave observatory, and also the first to use cryogenic mirrors. During an engineering run on the 18th of May, LIGO scientists say they already received a signal that was possibly caused by a neutron star being swallowed by a black hole. We'll have to wait a while for confirmation, but if these early results are any indication, LIGO is about to blow the doors of our understanding of gravitational wave-generating phenomena. So, what other developments lie ahead? India is preparing a collaborative project called LIGO India, or Indigo, which will help LIGO triangulate better location data. In 2027 to 2028, LIGO will implement its LIGO Voyager upgrade, which will achieve higher sensitivity with 4 times heavier mirrors and higher frequency lasers. And in the more distant future, a 3rd-generation facility has been proposed called Cosmic Explorer. This facility would feature 2 new observatories with arms spanning 40 kilometers and 20 kilometers, respectively. Remember, with interferometers, bigger is better. But the proposal that really excites me is the Laser Interferometer Space Antenna, or LISA. This would be the first space-based gravitational wave observatory, which would utilize 3 spacecraft, in a 2.5 million kilometers long configuration. This interferometer would be so big and so precise, scientists hope it would be adept at uncovering exotic and theoretical sources of gravitational waves, such as cosmic strings and other speculative phenomena. In theory, it could help us stare directly into the fabric of reality. With a planned launch date of 2037, we're still over a decade away, but it's never too early to start counting the years. So, there you have it, an overview of LIGO and how scientists are using gravitational waves to better understand the universe. They give us evidence of extremely remote and ancient phenomena that cannot be measured by other means. And they can be a secondary way to measure observations made by other instruments like the Webb telescope or Hubble. In time, this revolutionary field should allow us to understand the nature of our universe, its history, and even its future. I hope you found this episode as fascinating as I have. Tune into the universe with the right equipment, and you will hear it humming no matter where you look in the sky. Of course, it's not possible for sound to travel in a vacuum of space. Instead, we are talking about the hum of gravitational waves. You might already be familiar with a similar signal discovered decades ago. It's called the cosmic microwave background, and it is the afterglow of the Big Bang. This glow of microwave light was a groundbreaking discovery. It was the smoking gun that solidified the Big Bang's place as the leading theory of our universe's beginning. Yet this light signal had a glaring weakness. Despite it being the earliest light of our universe, it was emitted almost 400,000 years after the Big Bang. If we want to go back earlier, we will need a background signal made not of light, but of the ripples of the fabric of space-time. In 2023, astronomers at the Nanograph collaboration have announced that by using a clever trick, they may have detected just that. Using exotic stars as a galactic-size gravitational wave detector, they measured the faint hum of space-time itself. This hum of gravitational waves might just be the reverberations of the very creation of